Dear students, we keep on discussing our uh, discussion, or rather keep on discussing the idea of sequences. So sequence, if you look at it, it would look as if you look at it in R2 and you take n and put a coordinate as x1 and the coordinate as x2 and x3 and so on. One of the key things that we observe in a sequence, what we did in the case of sequence of real numbers and now in the case of sequence of vectors in Rn, how they behave. How they behave means where do they actually go? Is it that their norm remains within a certain limit that is greater than 0 and within some bounded by some k or p or something, some number, or the norm is increasing? Or it could be that I can say that the sequence of vectors, or if you want to even think about real numbers in your mind, that's better to do it. Does this sequence of vectors move towards some sequence? Pardon me. Does the sequence of vectors move towards some vector? Is it that the distance of the element, as we keep on increasing n, the distance of the members of the sequence, that is xn, from a given vector becomes less and less? This is what is something important, because that is what we have seen in the case of real numbers. For example, if you take the sequence which is called the harmonic sequence 1 by n, xn equal to 1 by n, you have 1 half the one which we had just seen here, this one. Now if you, as you keep on increasing the value of n, this 1 by n value keeps on decreasing and decreasing and decreasing, so this value is approaching towards 0. So this is something which we understand. So here the question is what we mean by the word that a sequence xn goes to a limit L, that the sequence of vectors xn is going to the limit L. What we mean is the following, that you can give me any epsilon, however small, doesn't matter. I can say that except a finite number of elements of the sequence, that is, I have a n0 cutoff. So x1, x2, dot xn0. From xn0 to any n beyond xn, xn0 to any n which n can increase towards infinity, the distance of xn and the vector L can be made less than your chosen epsilon. You give me an epsilon much smaller, epsilon dash, you give me a much smaller epsilon dash which is much less than your given epsilon, then only I can find another n0 dash which is possibly much bigger than the n0 I had chosen earlier when epsilon is very small, such that starting from x1 to xn0 dash, starting from xn0 dash, for whatever n you choose, the distance between xn and L can be made less than that epsilon dash. That is what is very important. So this n0 that you have depends on this epsilon. It tells you that as give me any distance you want, give me any number you want, I can show that except a finite number of elements of the sequence, or rather in another way to tell it in a twisted way, that when n is sufficiently large, I will always have the distance between xn and L, that is norm of xn minus L, to be strictly less than the number you have chosen. You can choose another smaller number. I can show you which are the n's, what is that cutoff n naught beyond which for all n this relation will hold. And if this happens, then we say of course xn is going to the limit L, which we write as limit n tends to infinity, xn is equal to L. This epsilon delta definition actually puzzles a lot of person. It really tells you that if a sequence of vector moves to towards another sequence, then one however small the distance you want, you will always find xn's, one cutoff value n naught, such that beyond that, for all xn's, that all xn's for all n beyond that xn's are within that distance from L. That is, they all cluster near L. That is the key idea, that except a finite number of elements, whatever distance you see, I will find a cluster of points around L within that distance. That is the key idea. When points behave in such a way, it's like that convergent point, limit point is kind of attracting the points. Except a finite number of them remaining, it keeps on attracting. And it's very large. It's the whole thing is in a kind of a sense of a zone of attraction of the value L. Now, as you study, you have to solve some problems. So in the notes which I have already sent you across in the mail, you would see that there are problems given in the lecture notes, and these are your assignments. And please understand, I have not given problem number 1, 2, 3, 4. It doesn't matter. I just written the problem means that is what you have to solve. So let us consider a sequence xn is converging to L. You have to prove that this sequence is unique. This limit is unique, not the sequence. So if xn converges to L, then there cannot be any L dash which is different from L, and xn would converges to L dash. So the same sequence cannot converge to two limits. And once the sequence xn converges to L, whatever subsequence you choose from xn, whatever, that subsequence must also converge to L. So this is something you should try based on this definition. When we have a Zoom meeting, we can have a discussion on this. Doesn't matter. We will do that. Now, when you have what sort of behavior sequences can have? If you look at a real sequence, either they converge or they diverge. Basically, their norm value becomes very big, that they move away and away and away and away from the origin. So that is, they zoom out to infinity. But there could be certain sequence that don't seem to zoom out to infinity, but they seem not to also be attracted by some point. They don't also seem to be converged. Such sequence are called oscillatory sequence. They keep on moving in and around some value. For example, the sequence -1 + 1 -1 + 1, that is -1 to the power n, is such a kind of sequence. -1 + 1 -1 + 1 -1 + 1, as it goes on. Now, a key idea is that of a bounded sequence. That a sequence xn is called bounded, that if there exists a k greater than equal to 0, such that norm of xn is less than equal to k. For example, all sequences, the values are 0. All the values are 0. So it's a kind of 0 function. For everything, the function value is 0. So then you can choose k to be 0. So that is why you have taken k greater than equal to 0. So norm of xn, the distance of xn is bounded. So that is, the things cannot just arbitrarily fling away as far as it wants from the origin. A convergent sequence has to be bounded, while every bounded sequence need not be convergent. For example, I will take the sequence -1 + 1 -1 + 1 -1 + 1 -1 by n. It is really not convergence, it's oscillating. It is bounded. That norm of x is less than equal to 1, k is 1, norm of any xn, mod of absolute value actually, because we were in the real setting. But it does not converge. There is no value to which it converges. Does it converge to 0? No. Does it converge to 1? No. Does it converge to -1? No. There is no value to which it converges. And I want you to figure out that the sequence xn equal to -1 to the power n, why it doesn't converge. You really have to show that it doesn't satisfy this definition, the epsilon delta definition of the convergence of a sequence. So that's very important. So now we are going to establish the fact that xn if a sequence xn is convergent, it must be bounded. So this is important theorem. So let us assume that xn converges to L. Since xn is convergent, whatever epsilon you give me, I can always find the cutoff n naught such that norm of xn minus L is less than that epsilon, strictly less than that epsilon. So here I chose epsilon equal to 1, any epsilon inside. So I can find an n naught depending on that choice, such that for all n greater than n naught, by definition this would be true. Now observe now that whenever I take n greater than n naught, I can write norm xn as norm of xn minus L plus the vector L. Now by the triangle inequality, norm of xn minus L plus L can be written as less than equal to norm of xn plus L plus norm of L. Now when n is greater than equal to L0, norm of xn minus L is always strictly less than 1. So norm xn here is strictly less than 1 plus norm of L. So it is bounded. So whenever for all values of n which is bigger than n naught, norm of xn is bounded by 1 plus norm L. L is a fixed vector, so its norm is a fixed number. So 1 plus norm L is say k dash. Now what about the other finite number of elements? Now this is very simple. What you do, you take the norm of x1, take the norm of x2, norm of x3, and up to norm of x n naught minus 1. Because beyond n naught and beyond, you know it is norm of xn values are less than 1 plus mod L. So now among 1 plus norm L. So among these values, there is n naught minus 1 values from here and this value. So among these n naught values, so take the maximum between 1 plus mod L and any maximum among them. Whatever is the maximum, take that as m. Then xn must be less than equal to m for any n. I am sure this is clear to you. For n greater than n naught, it is less than this. Suppose there is mod of x1 is bigger than, among all these n naught values here, the biggest number is norm of x1. So whenever n is greater than equal to n0, xn would be less than equal to 1 plus mod L, which would be less than equal to norm of x1 if you want to say. So norm of, so what, and anything else here is also less than norm of x1. So norm of x1 becomes my m. So this is very simple to understand. So this completes the proof. So now I ask you a problem for you to think. Suppose xn is going to be arbitrarily large. We call it a divergent sequence. But why you think that the sequence won't be converging? What is the reason? And what do you mean by norm xn growing to be arbitrarily large? Can you define yourself? Just think and try to define for yourself what is the meaning of this term. What happens if norm xn grows to be arbitrarily large? Now xn does not if xn is bounded, it need not be convergent. But there is an interesting result which tells you that every bounded sequence has a convergent subsequence, and hence the whole idea of subsequence becomes very, very important. So let me stop here today, and we will come in the next class for the famous Bolzano-Estrus theorem. We'll give a gap of a day so that it is all these 3 lectures today you have the time to go through carefully. And I will also give you certain suggestions in the mail. You should read that before we start the Bolzano-Estrus theorem, which says that every bounded sequence has a convergent subsequence. So there can be a convergent subsequence, it goes to some limit. There can be another convergent subsequence which goes to another limit. And if all such convergent subsequence goes to a fixed limit, then the sequence actually converges to a fixed limit. So this is something one has to understand. That's a very, very important idea, that every bounded sequence has a convergent subsequence. Thank you very much.